Hi, and welcome to the talk. I would like to tell you about our work on using automata learning to improve reinforcement learning. We will consider a special kind of automata called reward machines that are a good fit for reinforcement learning problems. Before starting, let me introduce the authors of this paper. Those are Bo, Yousef, Je, and Ufuk from UT Austin, and my colleagues from MPI for Software Systems, Daniel and Rupak. My name is Ivan. Consider a reinforcement learning problem in which the underlying Markov decision process is represented by this grid world. There is an agent that moves around the grid world, and some locations of the grid are marked by propositions A, B, C, or D. Those are the propositions relevant for getting rewards and are considered to be given. In this path, the agent went through A, B, C, and D. It always received a reward 0, and only upon visiting D, it received a reward 1. In a different path, it went through A, B, B again, C, and D, and in the end received a reward 1. When the agent went through A and then D, it received a reward -1. The same happened when it went through A, C, B, and D. It got a non-zero reward only upon visiting D, and that reward was -1. One thing is interesting here. The agent got different rewards based on different histories, and not the last state and action. In other words, these rewards violate a so-called Markov assumption, that the state of the MDP must include all information necessary for determining the reward. The question is then, how to define the state? One could include a portion of the history, but how long a portion? We do not know upfront. This question has received some attention in the literature already. And one good solution is to use automata or temporal logic to capture non-Markovian rewards. So, how would an automaton representation look for our example? Let's first capture the cases when we should get the reward 1. This automaton encodes that we have to see A, B, C with possible repetitions, and then upon seeing the proposition D, we get the reward 1. The labels on the edges define propositions and rewards obtained upon seeing these propositions. This kind of machine is in the reinforcement learning literature called a reward machine. Some of you may have seen it under the name Mealy machine in other contexts. This particular example is reducible to a deterministic finite state automaton, which is an important subclass that separates successful from unsuccessful executions. Now let's see what can go wrong. If we visit a state with the proposition D prematurely, we get the reward -1. Similarly, not respecting the ABCD order will send us in a state from which we can only get the reward -1 upon seeing D. With this automaton, we can define a state as a product of the automaton state and the environment state. The state defined in such way does indeed satisfy the Markovian assumption. A work from 2018 has shown that using reward machines has clear benefits over other methods of capturing history. They integrate reward machines with the standard Q-learning algorithm. There is one problematic assumption though. The machine needs to be provided by the user. This assumption is often not justified. Maybe the rewards are provided by sensor reading in the real world, or maybe the user is not able to encode their intuition about the reward into a reward machine. That is why, in this work, we lift the assumption that the user has to provide the reward machine, and we learn the reward machine through the agent's exploration. So, how do we do it? Let me give you an overview of the algorithm, which we name JIRP, an abbreviation for Joint Inference of Rewards and Policy. First, we initialize the hypothesis reward machine H. Concretely, we initialize it to a trivial machine with one state, and it always gives reward 0, as you can see on the right-hand side. Then we initialize a set of Q functions Q, one per state of the machine H. In this case, only one Q function, corresponding to the single state of the machine H. And finally, we initialize a set of counterexample traces X. In the set X, we will gather the agent's experiences that contradict the hypothesis machine H. Once these three variables are initialized, we repeat the following steps. First, we run an episode of Q-learning with reward machine, abbreviated by QRM. During the episode, the queue functions are updated as usual in QLearning. Additional output is the agent's experience, the propositions it has seen, as an example, let's consider A, B, C, D, and the rewards it obtained. In our example, a reward 1 upon visiting D and 0 otherwise. Then we check whether our hypothesis reward machine age matches the experience, that is, whether upon seeing A, B, C, D, it outputs rewards 0, 0, 0, 1. Since age never gives any non-zero reward, it clearly does not. Therefore, we are adding the experience to the set X. Then, we infer a new reward machine consistent with the set X. This reward machine, as you see from the label on the self loop, gives reward 1 whenever the proposition D is seen. In the paper, we present a reduction into the satisfiability problem for propositional logic. A solution to that problem yields a minimal machine consistent with the set X. This property of minimality is crucial for our optimal convergence guarantee. Finally, we reinitialize the set of Q functions. We repeat the procedure by performing another episode of QLearning with the reward machine. Assume that this time we saw labels AD and were rewarded by 0 and -1. Now again, we compare the experience with the current hypothesis. They are clearly not consistent. The machine age will always give us 1 upon seeing D. Thus, we add this experience to the set X and run the reward machine inference again. The newly inferred reward machine is now consistent with the set of experiences. We reinitialize the set Q again to have one Q function per state of the hypothesis machine age. And so we repeat the procedure until we reach the correct reward machine. In the paper, we prove that we will eventually do so. This was, of course, a high-level view of the algorithm. There are details that I didn't mention. Let me at least mention the two most important optimizations. First, we do not run the inference of the hypothesis machine every time we see a counterexample, as this would make the whole procedure too slow. Second, we don't throw away all that we learned when resetting the set of Q functions. Sometimes, if the two machines are sufficiently similar, some of the existing Q functions can be reused. This is, in short, our solution to the problem of learning automata representation for non-Markovian reward functions. Let's now take a look at the other works on similar topic. It turns out that this and the last year have been very fruitful in combining automata learning and reinforcement learning. The works most similar to ours have been by Carta and others from NeurIPS 2019, and concurrent with our work, Gaun and Brafman from AAAI 2020, and from the same conference, the work of Forelos Blanco and others. These three papers present slightly different problem formulations, which all end up in a solution that interleaves automata learning with reinforcement learning. They differ to each other in three dimensions. First, in the way they define the problem. Second, in the formal representation of rewards. And third, dependent on the first two, in the automata learning method that they use. Our algorithm overlaps with those three works. We solve the problem of non-Markovian rewards with reward machines and using passive automata learning methods. The best thing about our work in comparison to the related papers is that we provide an optimal convergence guarantee with a finite upper bound on the episode length. In the end, let's see how our method performs and what practical benefits does it bring. Our implementation is based on libAlpha SAT-based learning method for minimal DFAs. We compared the presented algorithm to QLearning in the space augmented with information on whether or not a proposition has been seen, hierarchical reinforcement learning with one option for each proposition, and deep reinforcement learning whose feature input are the past 200 propositions seen along the trajectory. We show results for a task in the Minecraft world scenario. We measure what is the average obtained reward at increasing number of training steps. The results for JIRP are shown on the leftmost graph, and at around 400,000 steps, it converges to reward 1, while other methods never reach reward 1. We tested on different tasks in the Minecraft scenario as well as in an autonomous vehicle scenario and an office world scenario. The details can be found in the paper, but the shared conclusion is that our algorithm converges faster than the competing methods. Thank you for your attention, and I'd be glad to answer your questions.